Picture a mammal that can hold its breath for 2 hours, not 2 minutes, 2 hours. While you've been listening to this, a Weddell seal somewhere in the Antarctic has descended nearly 2,000 feet below the surface. Above the surface, Antarctic air can plunge to minus 40 degrees Celsius, cold so severe that exposed skin freezes in seconds. Below the surface, the ocean hovers just below freezing, a constant grip that drains heat faster than any mammal can replace it. Its heart rate has dropped from 120 beats per minute to just 4. 4 heartbeats, barely alive by any measure we understand. And yet, it's hunting, navigating, thinking. This isn't an adaptation. This is a complete redesign of what mammalian life is supposed to be. We're going to talk about seals today. And I need you to forget everything you think you know about them. Because the deeper we look into these animals, the more we realize nothing about them makes sense. Not their blood, not their eyes, not the way their bodies respond to pressure that should liquefy their organs. Seals shouldn't exist, but they do. And the reasons why will change the way you think about evolution itself. Let's start with something simple. Seals are mammals, just like you. That means they breathe air, nurse their young, maintain a constant body temperature. They evolved from land animals, specifically from creatures that looked something like otters or bears, depending on which lineage you're examining. Around 50 million years ago, some of these animals began returning to the ocean. That decision created problems, big ones. When you dive underwater, your body fights you immediately. At 30 feet deep, the pressure compresses your lungs. At 100 feet, nitrogen begins dissolving into your bloodstream in the dangerous quantities. Go deeper, and the pressure becomes so extreme that your ribcage would collapse inward like a crushed can. Human free divers, the absolute best in the world, can reach depths of around 700 feet. But they train for years. They use techniques to pre-oxygenate their blood. They equalize pressure constantly, and even then, they're underwater for just minutes, not hours. A Weddell seal dives to 2,000 feet, regularly, sometimes deeper. And it does this dozens of times a day for its entire life, starting when it's just a few weeks old. So, what's different? Here's where it gets strange. Seals don't have larger lungs than you'd expect. In fact, their lungs are proportionally smaller than ours. That's the opposite of what you'd predict. You'd think an animal that dives for hours would need massive lungs, right? Giant air reservoirs? No, because seals don't store oxygen in their lungs. They store it in their blood and in their muscles. A seal's blood contains roughly twice the concentration of hemoglobin as yours. Hemoglobin is the protein that carries oxygen through your bloodstream. More hemoglobin means more oxygen capacity. But here's the trick. Seals also have something called myoglobin in their muscles. Lots of it. Myoglobin is similar to hemoglobin, but it's specialized for muscle tissue. It holds on to oxygen even more tightly. The muscles of a seal are so dense with myoglobin that they're almost black. If you were to cut into a seal's tissue, it wouldn't look red like beef or chicken. It would look dark, almost purple-black, like the flesh of a tuna. That's not normal for a mammal, but it works. A seal's muscles become an oxygen storage system, a biological scuba tank woven directly into its body. Still, that only explains part of the mystery. Because storing oxygen is one thing, using it efficiently is another. When a seal dives, something happens that would kill you. Its heart rate drops. We already mentioned that, from 120 beats per minute down to 4 or 5. But it's not just slowing down randomly. The seal's body is making a choice. It's deciding which organs get oxygen and which ones don't. Blood flow to the periphery, limbs, skin, digestive system stops almost completely. The seal's flippers go cold. Its intestines shut down. All available oxygen is redirected to 2 places, the brain and the heart. Everything else is allowed to go anaerobic. Anaerobic means without oxygen. Your muscles can do this for short bursts. That's what happens when you sprint and feel the burn of lactic acid building up. But you can't sustain it. Lactic acid is toxic. It makes your muscles seize. It acidifies your blood. If it goes on too long, it kills you. Seals do it for 2 hours. They accumulate lactic acid in their muscles and tolerate it. When they surface, their body clears it out, processes it, resets. Then they dive again. This isn't just impressive, It's biochemically impossible by the standards of most mammals, and we still don't fully understand how they survive it. One theory suggests that seals have specialized enzymes that buffer lactic acid more effectively than ours. Another theory points to their kidneys, which may be able to filter and neutralize the acid faster. But these are educated guesses. The truth is, we're still uncovering the mechanisms. What we do know is this: a seal's dive reflex is so extreme that it borders on controlled death. And that's just the beginning. Now, let's talk about pressure. At 2,000 feet underwater, the pressure is roughly 60 times what you experience at sea level. 60 atmospheres pressing inward on every square inch of the seal's body. Your lungs would collapse, but remember, seals have small lungs. And here's why that matters. When a seal dives deep, it exhales first. It empties its lungs before descending. This seems counterintuitive. Why would you get rid of your air supply? But it's brilliant. By exhaling, the seal removes the air pockets that would compress under pressure. No air means no compression. No compression means no risk of lung collapse. But it also means no oxygen from the lungs, which brings us back to the blood and muscle storage system. The seal isn't breathing underwater. It's not extracting oxygen from its lungs during the dive. It's running entirely off stored reserves, like a battery. And those reserves are finite. So, how does a seal know when to turn back? We don't have a complete answer, but research suggests that seals have some kind of internal oxygen sensor, probably in their brain or major blood vessels, that monitors how much usable oxygen remains. When it hits a critical threshold, the seal stops hunting and ascends. It's a calculated risk every single time, but here's the truly disturbing part. Seals don't just dive in shallow coastal waters. Elephant seals, those massive blubbery creatures you might have heard about, dive to depths exceeding 5,000 feet. Some researchers have recorded dives approaching 7,000 feet. At that depth, the pressure is 200 atmospheres. The weight of the ocean pressing down is equivalent to having a fully loaded semi-truck sitting on every square inch of your body. And the seal just swims through it. Its bones don't shatter, its organs don't rupture, its blood vessels don't burst. How? Part of the answer lies in flexibility. A seal's rib cage isn't rigid like yours. The ribs are connected by cartilage that allows them to compress. As the seal dives deeper, its chest cavity literally shrinks inward. The lungs collapse completely. Not catastrophically, but in a controlled way. The rib cage folds around them like a protective cage. It's reversible. When the seal ascends, everything expands back to normal. But that's just structure. There's also chemistry. Nitrogen is a problem for human divers. Under pressure, nitrogen dissolves into your bloodstream. If you ascend too quickly, it forms bubbles, like opening a shaken soda bottle. Those bubbles can block blood flow, damage tissue, cause paralysis, or death. We call it decompression sickness, the bends. Seals don't get the bends. Why? Because they exhale before diving. No air in the lungs means no nitrogen to absorb. But even more than that, seals have a trick in their blood itself. Research suggests that their blood chemistry, possibly involving specialized proteins or lipid molecules, prevents nitrogen from dissolving as readily as it does in humans. It's like their blood is chemically resistant to the physics of pressure. We're still studying exactly how this works, but it works. And then there are the eyes. If you've ever seen a seal up close, you've probably noticed them. Large, dark, almost hypnotic. Those eyes aren't just for show. Seals hunt in near total darkness. At 2,000 feet, sunlight is gone. The ocean is black. The only light comes from bioluminescent creatures, tiny sparks of living glow drifting through the void. A seal's eyes are adapted to detect that light. The retina of a seal is packed with rod cells, the photoreceptors responsible for low-light vision. Humans have rods too, but seals have them in far greater density. Their eyes also have a reflective layer behind the retina called the tapetum lucidum. It's the same structure that makes a cat's eyes glow in the dark. Light passes through the retina, hits the tapetum, and reflects back through the retina a second time. This doubles the amount of light the eye can capture. In pitch blackness, a seal can see things you couldn't even imagine. But here's the problem. Those same eyes also need to work in bright Antarctic daylight when the seal is on the surface. The contrast is extreme, from absolute darkness to blinding snow glare. So seals have a pupil that can constrict to an almost invisible pinpoint or dilate to cover nearly the entire eye. The range of adjustment is extraordinary, far beyond what humans are capable of. But even that's not enough, because water bends light differently than air. When you open your eyes underwater, everything is blurry. That's because the refractive index of water is close to the refractive index of your eye's lens. Your lens evolved to bend light in air, not water. Underwater, it doesn't work correctly. Seals solve this. Their cornea is flattened and their lens is almost spherical. This compensates for the refractive difference. A seal can see clearly underwater and in air. Most animals can't do this. Most animals that live in water have terrible vision on land and vice versa. Seals have both. It's not a compromise. It's a complete dual system. So, let's take a step back. We've talked about oxygen storage, pressure resistance, lactic acid tolerance, optical adaptation. Each of these is extraordinary on its own. But here's what keeps evolutionary biologists awake at night. All of these systems had to evolve together. You can't have a seal that dives deep but doesn't have the oxygen storage to survive the dive. You can't have oxygen storage without the circulatory shutdown to conserve it. You can't have the shutdown without the biochemical tolerance for lactic acid. You can't have any of it without the flexible ribcage and pressure-resistant blood chemistry. Every piece depends on every other piece. This is what scientists call an irreducibly complex system, though that term is controversial. But the concept is real. You can't evolve halfway to being a seal and survive. A half-adapted seal drowns. A seal that dives deep without the right blood chemistry dies of the bends. A seal that stores oxygen but can't manage pressure gets crushed. So how did this happen? The traditional answer is gradualism. Small changes over millions of years. A slightly better oxygen capacity provides a slight advantage. Over time, the advantages stack. And that's probably true. But the speed at which seals evolved is unsettling. 50 million years sounds like a long time. And it is, by human standards. But in evolutionary terms, it's a blink. The transition from land mammal to deep-diving seal happened relatively quickly. The fossil record shows semi-aquatic ancestors, sure, but the leap from swims sometimes to survives at 7,000 feet underwater is staggering. It suggests that evolution, under the right pressures, can do things we don't fully appreciate. The ocean is not a forgiving environment. It kills fast. And yet seals didn't just adapt to it, they mastered it. They became creatures that can exist in a state most mammals would consider death. So, what does this mean? Why should you care about seals? Because seals represent something deeper. They show us that life is not fixed. It's not locked into one way of being. The rules we think are universal. Breathe constantly. Keep your heart beating. Maintain steady blood flow. Those aren't rules. They're just the default settings for our environment. Change the environment, and life rewrites the code. Seals live in a world that would kill us in minutes. And they don't just survive it, they thrive in it. They raise pups in it, they've built entire societies around it. And they did it by breaking almost every rule we associate with being a mammal. Medical researchers are studying seals now, trying to understand their oxygen storage, their pressure tolerance, their resistance to hypoxia, the state of oxygen deprivation. Because if we can figure out how a seal survives 2 hours without breathing, maybe we can apply that knowledge to human medicine. Stroke victims, heart attack patients, people in respiratory failure. The seal's body might hold answers we desperately need. But there's something else, something more philosophical. Seals remind us that evolution doesn't care about our expectations. It doesn't care about what seems possible or impossible. It just responds to pressure, to need, to environment. And given enough time, enough pressure, life will find a way. Not by bending the rules, by rewriting them entirely. So, the next time you see a seal, lounging on a rock, seemingly lazy, almost comical in its awkwardness on land, remember what it is. It's an animal that can shut down its heart, that can crush its own lungs and reinflate them. That can see in darkness deeper than any light has ever reached. That can survive pressures that would obliterate you. It's not a cute ocean puppy. It's one of the most extreme organisms on Earth, and nothing about it is normal.